This video documents the making of my desktop CNC mill, as well as some of the design choices and challenges I encountered along the way. I opted to use aluminium extrusion for the frame, as it is stiff and would give me a high degree of flexibility for mounting and connecting parts. It also fit nicely with the cheap linear motion assemblies I chose for the core of the build. In order to keep it as rigid as I could, I cut a sheet of aluminium to size and fitted it in the base. I used some acrylic sheets for the side panels to keep the chips contained. Throughout this build, I've used 3D printing to mount different parts to the frame. With the frame roughly assembled, I turned my focus to the electronics. I found this to be one of the most challenging parts of the build, with by far the most time spent troubleshooting. I used an Arduino running Gerbil for the control system. I made a rough housing using screw terminals to break out the pins. This kind of worked, but I ended up replacing it. I then wired in a 12-volt power supply and the stepper drivers. I used a fused and switched kettle socket to bring mains power into the machine. With everything wired in, I gave it a test drive. It was about this point it dawned on me that I had created a large lever with my Z-axis, which as you can see flops around like a wet noodle. This deflection has been by far the greatest mechanical challenge with this design. My initial attempt to correct this involved some 8mm ground rod and some cylindrical bearings to support the Z-axis further down its length, effectively shortening the lever. This helped a bit, but given the cutting forces it would experience, I was skeptical that this would do the trick. Nevertheless, I was keen to try cutting and printed up a mount for the spindle. Given my tool and skill limitation, I've used plastics in quite a few places I'd have rather had metal. In an attempt to reduce the impact on the machine's stiffness, I've done my best to use them in compression where possible and consider the direction of the layer lines. I improved a bit on this spindle mount later, but it and much more of the machine could stand to be metal. I exported a toolpath from Fusion 360 and after a dry run tried cutting some acrylic. It was rewarding to make some plastic chips and to see the machine functioning. It was quite loud though. The results weren't really the high precision part I had hoped for. Due to the deflection at the cutting head, the part came out of size, much more so in the y-axis than the x-axis, where there is less flex. I then gave it a go in some aluminium. This was very loud and I broke a few end mills in the process. It did nonetheless cut. It was clear that for the machine to be useful to me, I'd need to dramatically reduce the deflection. I swapped the 8mm rod for 12mm in the y direction and used a linear rail on a piece of extrusion for the x. I also reinforced the linear assembly with some additional bearings to spread the load further down the rod's length. I connected everything together with some custom laser cut plates. This really tightened things up a lot at the cost of a reduced working volume. With the machine more rigid, it was time to turn my attention to the electronics. Up until this point I had been unable to run the mill with limit switches enabled. Whenever the spindle span up, it would trigger the switches. I imagine the electrical noise produced by the spindle induced enough current in the adjacent wiring that those pins on the Arduino would read high. This meant that the mill didn't know where it was in 3D space, and I had to hover over the emergency stop in case I had instructed it to crash into itself. After some time researching other CNC projects that used Arduino, I found a solution using octocouplers. This part basically smooths out the signal, making it less sensitive to current spikes. I decided to integrate this into a PCB that would plug directly into the Arduino. This let me clean up the cables somewhat. Naturally, I wired the first PCB wrong, so it triggered all axes at once, but it worked as intended on my second iteration. Homing now worked, and I could define the size of the work area, as well as calibrating the motor's steps per millimeter. I mounted the loose parts to the frame and reinstalled the side panels and door. I ran a toolpath in some acrylic, making a pocket, drilling a hole, and cutting along a contour. The resulting part was a great improvement over my previous attempt, though the remaining deflection still led to the part being a little undersize. It was at this point I realized that the moment at the spindle mount itself was likely contributing to the deflection, and that mounting these supporting bearings higher up would reduce this. I printed up a quick adapter to test this, and saw that the deflection was further reduced. The measured deflection at the toolhead, with me pushing as hard as I can, is around 0.5 in the y direction and 0.3mm in the x. This test piece came out on target in the x direction, but slightly undersized on the y. I noticed that some of my old prints had begun splitting along their layer lines, so designed a new part that used several pieces. This let me orient the layer lines both tangentially to the spindle and the screw heads. Hopefully this will last longer. Cutting aluminium is possible, but is very loud and not particularly precise. The rigidity of this design is its largest limitation. I think with some more tuning though, I'll be able to get some workable results in softer materials such as woods and plastics. Having gone through this process, I have learnt a lot, and have many things I would do differently next time. I'm particularly interested in reducing the part count while optimizing for stiffness and noise level. It would be really cool to be able to produce metal parts at a reasonable tolerance in the home environment. I'm really fascinated by digital manufacturing and the power that it puts in individuals' hands. Materials and shapes that were previously only achievable by industrial processes are now within everybody's reach. I hope to develop this idea further and perhaps eventually create plans for an open source CNC mill that could feasibly be used in the home, much like we use 3D printers today.